take a look at some special systems of linear equations. The typical system of linear equations that we've been looking at are two lines that intersect. And when the lines intersect, they have one solution. There's one point where they cross over, and at that point, that solution works for both equations. So it's our one solution for the system. But if the lines are parallel and they never cross over, they never have a point that works for both equations. So they'll have no solution. There are also times when the system is two or more lines that are exactly the same line. So they are on top of each other and they literally share every single coordinate point. So they have infinitely many solutions. So we've got some special systems of linear equations. We can have parallel lines which have no solution, and we can have lines that are the exact same line and have infinitely many solutions. So let's take a look at our first example here. So we're going to look at solving these problems two different ways. So our first set of linear equations here is y equals 2x plus 1 and y equals 2x minus 4. So we're going to graph these and we're going to solve them by substitution and see what happens. Graphing is a good way to start because we get a picture of what these equations actually look like, and graphing is good for estimating our solutions. So I'm going to start with my first one here. I see it as a y-intercept of positive 1, and my slope is 2. So up 2 over 1, up 2 over 1, or I could go down 2 and back 1, down 2 and back 1, and then I'm going to connect these dots in a straight line. My second line has a y-intercept of negative 4. It also has a slope of 2. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I'll connect these guys. And it looks like I've got parallel lines here. They're not running into each other. So it's looking like we have no solution here. But let's test it out by actually solving this system using another method. Let's also use substitution. Both of these are solved for y. So I'm going to start with y equals 2x plus 1, my first equation. And for this y, I'm going to sub in 2x minus 4. So now what I'm going to do is I'm going to try to solve this system. So if I subtract 2x to get rid of the x's on this side, well, they cancel out on both sides, and I actually end up with negative 4 equals 1, which I know is never true, so I don't have any solutions. So we've tried two different methods. We get no solution for both of them, so we know that there isn't a solution for this system. Anytime we see that our lines have the same slope, they're parallel, we're not going to have a solution to our system. All right, let's take a look at another system. So here we have negative 2x plus y equals 3 and negative 4x plus 2y equals 6. So I'm going to change these guys so that they're in slope-intercept form, so they're a little bit easier to graph. So for this first one, I'm going to add 2x to each side, and I will get y equals 2x plus 3. This one's a little trickier. I'll start by adding 4x to each side, which would give me 2y equals 4x plus 6. And then I will divide everything by 2. So I get y equals 2x plus 3. And I notice, even before I've done any graphing, they're the exact same line. So I'm only going to have to graph it once. So my intercept is at 3. My slope is 2, so I could go up 2 over 1, but that'd already be off my graph. So I'll do the exact opposite. I'll go down 2 and back 1, down 2 and back 1, down 2 and back 1, and I will connect my points. Now, because these two lines would lie exactly on top of each other, they're sharing all of the same coordinate points. So here I have infinitely many solutions. Basically, an infinite number of solutions. I could just keep coming up with them since the lines are going on forever. So let's also see how we would solve a problem like this using elimination. So I've got my two equations. I want to be able to eliminate one of my variables. So what I'm going to do is I'm going to multiply this top set here by -2, which is going to give me 4x minus 2y equals -6. And the reason I chose that was because I want to eliminate a variable, and I was thinking if I multiply this by -2, I'll get positive 4x, and -4x will cancel out. But when I look at my actual equation, what I notice is not only do my x's cancel out, but so do my y's. So I'm left with nothing here. And -6 and 6 is also nothing. So I get 0 equals 0, which is true in every instance, and something that is always true means I have infinitely many solutions. So anytime I notice that the equations in my system represent the same line, I'm going to have an infinite number of solutions. All right, so let's take a look at an actual real-life problem. So we've got a trapezoidal piece of land here that is 48 kilometers, a rectangular piece of land that has an area of a perimeter of 144 kilometers, and we want to write and solve a system of linear equations to find the value of x and y here. So in this first one, I can see that I've got 2x and 4x, so 6x, and I've got 6y and 6y, or 12y, and my perimeter here is 48. For my rectangular piece of land, I've got 9x and 9x, or 18x, and I've got 18y and 18y, or 36y, and it equals a grand total of 144 kilometers. So we can use any method we want here to solve this system of equations, but I think I'm going to use the elimination method. So I'm going to take this equation right here and multiply by -3. The reason I'm choosing -3 is because I see 18 here. I know if I multiply -3 times 6, I'll have -18x, and they will cancel each other out. So I'm trying to get something to cancel here. So I get -18x minus 36y, and that's going to equal 144. Oh, sorry, negative 144. Oops. And my other equation is 18x plus 36y equals 144. Oh, so once again, even though I was just trying to get one of my variables to cancel out, both of them cancel here. So I'm left with nothing. And over here, negative 144 and 144 is 0. So in this case, we have infinitely many solutions.